I just wanted to make a few announcements before Nate talks to you about your next lab. And I know this, just want to remind you all that you have an exam this Thursday. You don't have a lab this week. You have an exam this Thursday at 8 o'clock. And I just wanted to post a few things. Number one, Robert Wagner is going to be doing office hours today from 10 to 11. It's posted under announcements, so there is somewhat of a conflict with my office hours. So just want to let you know, Will Davis, Yuha Yu, and Alex Moeller, if you want to attend those office hours, I would say that's a higher priority than my meetings, but just let me know so that we can reschedule you for another time. It's totally up to you. Again, the office hours for Robert are posted, and I will actually, let me see, if you go to this posting on February 10th, there's the Tuesday, February 15th from 10 a.m. to 11 a.m., there's the link, and tomorrow from 10:30 to noon, again, office hours regarding problems associated with what might be on the exam. Robert and I have been working for quite a few weeks to put this exam together. It will be, I think, a very interesting exam. You will be looking at a robot, state-of-the-art robot that we've reversed engineered to some extent because clearly the manufacturer did not share anything with us. So it's our best guess as to how it works, and I think you will learn a lot from the exam. I always like to put together an exam that is a learning experience and not just an examination experience. So anyway, these are the office hours from Robert. And the other thing is, I do want to know, let me put something else on the screen over here. Let me put this back, and I just again want to remind you about the exam this coming Thursday. You can come here and take the exam in ME 212. I would say to you that if your apartment or your home, wherever you do these things, has a poor Wi-Fi connection, please come here. Okay? Don't stay there, because if you have a poor Wi-Fi connection, that's not a good thing. Okay, so do come here. The exam will be ready and posted. You'll be able to download it at 8 a.m. on Thursday. You will have essentially from 8 a.m. to 9:55. And we're going to give you 10 minutes to sort of scan everything and get it in to the system through Canvas. Those of you who, for whatever reason, want a printed exam, I've had 2 requests. I'm okay with it. I will have a printed exam available for you, but I need to know in advance. I'm not planning on printing 52 exams and bringing them here, just a waste of good resources. So anybody who wants to have a printed exam has to come here, and I will provide a printed exam. So please email me. I've had 2 requests over the last 24 hours. That's fine. But if you don't request one, I will not have one available for you on Thursday. It's totally up to you if you want to have a printed exam. It will all be available to you for download via Canvas, and once it's downloaded over Canvas, you can actually work and enter all your information right into the exam. So that's up to you how you want to proceed. Okay, so without further ado, this, by the way, I downloaded on the course website, so you can read this again as many times as you like. So this is also posted on our course website under lectures, because it's part of consider it the beginning of my lecture for today. Anyway, without further ado, I'm going to pass the baton, which is the microphone, and the laptop, right?
I'll show you mine or yours.
Use yours.
All right. Hey guys, I'm Evan. I'm one of the lab TAs, and just going to introduce Lab 4 today, which is the assembly of a small handheld flashlight. So a couple things wrapping up Lab 3. We want the relay reports in Friday, February 28th by 8 a.m. So that's not this Friday, but a week from then. And this Friday, actually, we're going to be transitioning the lab over from Lab 3 to Lab 4. So if you need to make up any work on Lab 3, Robot 3 will still be set up for you, but Robots 1 and 2 are going to be on Lab 4. And then finally, if you have any lab questions, email both myself and Nate and Nick, because if you email all three of us, we'll be able to get a quicker response for you guys, okay? So introducing Lab 4, we have 3 weeks for this, but kind of 4 weeks because spring break falls right in the middle of the lab, and we as TAs aren't really going to be around, but the lab is going to be open and available during your normal lab times if you need that extra week to work on this lab. But it isn't required or expected that you show up for the week of spring break. So the main objective of the lab is using the UR55 and a pneumatic chuck, which I'll explain a little bit in the future, to assemble this small flashlight assembly. Now for the pre-lab, like previous labs, you're going to have a little bit of coding to do, but it's really important for this lab that you try to have as much of the coding done as possible going into the lab, because this lab does take a lot of time. There's a lot of tweaking and fine-tuning that you need to do to really get your code performing the way you want. So if you can have pretty much everything coded going in there, and then just need to change timing or the coordinates for some moves, that'll be really helpful in making sure that you guys complete this lab in time. So this is a picture of the flashlight, and there are 4 different sub-assemblies on it. The head, the barrel, the battery, and the tail cap. And each of those 4 sub-assemblies will sit in this tray. This is just a thin piece of aluminum that sits on the UR5 table, kind of similar to Lab 3 with your ping pong balls and golf balls. And that'll just ensure that all of those flashlight components will be in the same spot every time you want to run your assembly code. So there are 3 different coordinate frames used for the lab, the robot, the chuck, and the flashlight tray. And this information will be more in detail in the appendix of the lab manual, which is going to be uploaded to Canvas shortly. So this is just a suggested order for how you go about assembling the flashlight. You don't necessarily need to follow this order, but this will give you a good idea of what we found is the best sort of set of operations to assemble it. So you need to grab that flashlight head, put it in the chuck, close the chuck, and then you're going to be threading on the main body of the flashlight. You're going to be putting the battery assembly within that main body, and then you're going to be putting the cap to the flashlight and threading that on. Now, we are using a new command in this lab, which is Tighten Torque. It's a function that uses the gripper we used in the last lab to tell how much torque is being exerted when you're threading your flashlight. So that can be a little finicky to get working. So taking the time to try to figure that out and get it working is going to be important. But that'll ensure that you've tightened everything properly without over-tightening it. So the grading is going to be done taking into consideration a couple different things. Creativity is an important one. It's going to, you're going to have the opportunity to make some kind of creative addition that'll allow your rollback to function a little bit better or faster, or just improve the assembly process. And we're intentionally a little bit vague about what we want to see for that, because we want to give you guys a chance to really come up with your own ideas and creative things. But some things that have been done in the past are custom fixturing, tooling, robot movements, control code, that sort of stuff. Personally, what I did for mine was we had a specific type of custom fixture that made the assembly a little bit easier. And then we also had some minor improvements in the code that sped up our assembly process. So yeah, when you're going about this lab, what you want to do is you kind of want to break it up. And the first thing you need to do is start assembling at slow speed. This will give you a chance just to make sure that your full assembly is working before you start trying to speed it up and get it within certain time frames, because another consideration for grading is going to be how long your assembly takes. We're going to have a few different time breakpoints and points associated with that. So it's going to be important that you guys iterate through the code and try to see how much time savings you can find in there. So a couple more notes. Be aware of the cables, especially since we're doing these threading operations with the gripper. You need to make sure that you don't over-rotate the gripper and strain the cables that are attached to it. And let us know as TAs right away if something breaks. The one exception being the flashlights themselves. It's really easy to strip the threads on them. So if that happens, we're going to have additional flashlights available for you guys to use and abuse. So that's good. But if anything else breaks, please just let us know and we'll come fix it, okay? Another note is that the pneumatic chuck that I was talking about earlier, that's what actually clamps and holds your flashlight assembly in place during assembly. And it's impossible to actually close the chuck without the head inserted into there, because if it did, it would break the chuck. So we have a light sensor to identify if the flashlight head is actually in the chuck. And I think there's a picture later in this presentation, so I can show you what I'm talking about. Okay, so talked about earlier, two big considerations in grading, outside of just actually having the flashlight assembly working, is going to be making sure that you do it as quickly as possible and try to hit the time targets that we're going to be setting for you guys. And then having creative additions is going to be important. So, yeah, as I said earlier, focused on getting the flashlight assembled however long it takes, and then just slowly iterating through and trying to cut time and improve the program. So with that, we kind of broke down some suggestions for you as to checking your progress week by week. So week one, you want to have your pre-lab coded and everything going in there, and then just try to get your program working as best as you can. Make sure that you have all of your coordinates updated and it's moving to the correct locations at the correct time. And start playing with the pneumatic chuck and the torque thread operations to really make sure you understand and can figure out how to use those. Then week two, you should really try to have your full flashlight assembled by that point, regardless of how long it takes. You should start looking at implementing your creativity ideas at this point too, see what you can do. And if you have some extra time, just try to keep refining your robot movements. As said before, spring break, there's no required lab, but the lab will be open if anyone needs that additional time. And then week three is when you're going to want to really take the time to implement your creative additions, refine the process, cut speed as much as possible, and then take a little bit of time to make your demo videos, because we are going to be requesting that you submit a full video of the flashlight assembly. And I actually have that video here. So this is a video of my robot from last year assembling flashlight. Oop. There you go. So the video starts at the move home operation. It's where the time begins. This is as soon as you hit that move home. It's placing the flashlight head in the chuck there. And then it closes the chuck now that the chuck realizes that there is something in there. Now we're grabbing the body and we're going to begin the threading operation for putting the body on the flashlight head. You'll find that the threading operation takes quite a while.
Your video should have audio on it, which is, you should describe what is unique about what you're doing in your video as well as in your report. Notice the dangling wires. You need to be very careful about not pulling out wires during any motions that the robot is doing.
Yeah, that's why when you're threading, you need to turn it part of the way, then back it up and turn it part of the way. You can't just keep it rotating because of those wires. That right there is a Titan torque operation. So it found that it made it to the specified torque of 3 newtons, so it stopped rotating and moved on to the next step, which is inserting the battery assembly into the flashlight. And then the final piece is the cap, which is another threading operation. Now the assembly is complete, and it moves home, and timing stops. Now one thing we want in your video is you demonstrating that the flashlight still works and is functional and you didn't break anything in the process. As we just disassembling it to show that, hey, I didn't strip the threads, the flashlight is still there. Okay. So deliverables, we want a full lab report. So in the past you've been doing memos, but this will require a full lab report, abstract, introductions, methods, results, discussion, and conclusion. And I believe we have a template or a guide available so you understand the requirements for a full lab report. We need to make sure that we're identifying what the unique contributions are, both in the and as Dr. Donath mentioned, during your video of the flashlight assembly. And then in the lab manual, as similar to previous labs, there's going to be a number of questions that we're asking you guys to answer. Now, put all of that in a zip file, upload it to Canvas, PDF of your lab report, all your robot files. That's going to be your RoboDecay file, your Python, that sort of thing. And then, as I showed you, a video of the assembly with commentary describing what the robot is doing and what the unique or creative aspects of your assembly are. So the lab is going to be due March 25th at 8 a.m. Have all your files uploaded then. Any questions? Yep.
So are us and our lab partners submitting the same video, or just one of us submits a video?
You're submitting the same video. Anything else? Any comments, Dr. Donath?
Your report should also identify who on your team did what. I think that's spelled out in the guidelines and the deliverables, but just make sure. I don't expect you to all write your own code for every part of the assembly. I assume you'll divvy it up, and one person will write some of the code, another person will write another part of the code, but you need to identify who did what. And obviously, each of you are going to be evaluating and testing the code from your partner. So again, identify who did what for the assembly. And I don't want to see one person doing all the software and another person doing whatever else there is. You must divvy up the software so the two of you, one of you does some of it, the other person does another part of it.
Okay. And just to be clear, the lab report itself, the submissions of those are independent, so each partner will submit their own. All right, thank you.
Okay. I'm always surprised that this room, which has been renovated, doesn't have more power outlets. My laptop has a problem with it. It won't work unless even though the battery's fully charged, it does not do anything if it's plugged in. Anyway, I haven't had the time to go figure it out or fix it. So anyway, and there's only one outlet in the back and outlets right here. Weird. Okay, we're going to go back and just want to refresh your memory what we were doing. And again, this is just a generic task. I don't really care if it's picking up a pin or holding a welding torch or holding some type of other element, whatever the end effector is. This idea, this way of breaking up the task into steps and homogeneous transformation matrices become very important. And it doesn't matter which robot you're using. They may call the position and orientation a pose. They may call it a target. There's all sorts of different nomenclature, different words used to represent what we're talking about here. So we're going to talk about a task, and the whole point behind this exercise that we're going to go through is to set up the equations so that the robot controller can solve them and thereby create a sequence of motions of the robot end effector that will meet the task at hand. So in this particular case, again, nothing magic about a pin, but it happens to be a pin. It's on a work surface, on a table. There's a coordinate frame on the table or the conveyor belt, and essentially there's an end effector. It's going to come down, grab the pin, and then swing it around and move it into a hole which is identified with respect to a block, and they each have different coordinate systems. Again, this is maybe more complicated than some tasks and maybe less complicated, but it's just illustrative. So we're going to generate what I will admit to you is many more transforms than you may need for a particular tasks. But the point here is so that you see all the elements and how they come together. And you will see we haven't come to that step, but we will be able to group certain combinations of homogeneous transformation matrices and give them a name, and you will see how that name plays a role later on. So again, the world coordinate system, the base coordinate system, whatever you want to call it, is somewhere identified by O or 0, and then there is a homogeneous transformation matrix that points to the coordinate system of the robot, wherever it is in the robot. Every robot has its own favorite place for its coordinate system. T6 is going to be a very important element in all of this. T6, again, is a 4x4 matrix, and that 4x4 matrix is going to identify where the flange of the robot, where the end, where the robot is, where you attach end effectors. It's going to tell us where the end is sitting out in space. And if you remember, if this is a 6-degree of freedom, a 6-jointed machine, then by solving the inverse kinematics of homogeneous transformation T6, which has a 3x3 rotation matrix, a 1x3 position vector, that combined in a homogeneous transformation matrix is going to tell us where the gripper's coordinate frame is. And if the gripper coordinate frame, the gripper itself, different grippers may look differently, and they may have various different homogeneous transformation matrices representing them, but they're with respect to the base or the flange, whatever you have on that particular robot. That's what E is all about. It's the end effector's homogeneous transformation matrix offset from wherever the end of the robot itself is. Now, typically in this world we're discussing, there's an object somewhere in space. That object may have various features identified with that object, just like there are many holes on that block. And so the features may represent different places on the block. And then we're going to have this other matrix here called G. And G is basically, think of it as the connective tissue. Maybe, I don't know if that's a good word to use here, but it basically allows you to make sure that whatever homogeneous transformation matrix, whatever position and orientation you're pointing with E, we will get all of it closed up so that we have this particular equation. So G allows us to form this equation that basically says that each of these is a 4x4. So Z times T6 times E is going to be equal to OBJ times F times G. If we didn't have G, then where on the feature would we be attaching? Where would we be pointing with this E? So let's now put some more specificity into this definition. We're talking about moving to a position over the pin. Let's call that P1. We are approaching the pin from overhead. We've talked about that before. And then we're going to close our fingers around the pin. We're going to lift it vertically from the surface. We're going to move it above a hole with the pin oriented along the hole. And then we're going to insert it, slide it into the hole. We're going to then let go of the pin, and then we're going to move the gripper away from the pin. And that's essentially the sequence of tasks we're going to go through right now. And so we're going to have to define a whole bunch of homogeneous transformation matrices. One is the pin's coordinate frame. I'm basically reviewing what I talked about the other day. So P is the pose of the pin in the base coordinate frame. B is the block's coordinate frame, again in the base, in the O coordinate frame. There's going to be the hole. There may be 10 holes, 4 holes. So this is going to be the ith hole with respect to the block. PG is what we're going to spend some time talking about, and it's going to be defined by E. This is essentially the approach above the pin when we first arrive. PD is a departure above the pin. This is an approach above the hole where it's aligned with the hole, and then we push it in, and that's the pose of the inserted. So I talked about this the other day. I'm not going to repeat this part. We did talk about it. I just wanted to point out that we have a lot of freedom in defining the coordinate frame, the pin's position and orientation in space. We can call it anything we want. And so what I said the other day, hey, let's just say that the coordinate frame associated with the pin, let's just say that it's somewhere down the axis of the pin. Let's call X the axis along the pin, Z to be pointing straight up in the vertical direction, and Y, in effect, is going to be, remember we defined the y-axis as the orientation vector, where our gripper, the axis of the gripper opening and closing, is a y. So we've automatically helped ourselves by defining the pin's axis coordinate frame so that the y is immediately aligned along the pin's axis. So essentially, now I'm going to get into a little more detail. So in other words, P is going to take us from the base coordinate frame to where the pin is in space. We see it over here. Now, you'll notice that P points to the center of that particular pin. Again, we can pick any place, but for right now, we're assuming it's pointed to the center. Now, keep in mind that we also have a gripper coming down, and that gripper is, we've picked the gripper, we've attached the gripper to the flange of the robot, and it is now going to define a coordinate frame. E is a homogeneous transformation matrix from the flange, from its base coordinate frame, and it is going to point to a particular location, wherever, in this case, it's pointing to the surface of the table on which the pin rests. That means that PG has to also go from P down to the same location where E is located. Now, if this is all there was to it, you wonder, why are we doing this craziness? But we have to remember that each one of these terms is a 4x4 matrix. It doesn't represent just a vector. A vector just has an x, y, and z component. We're talking about also in capturing the orientation at this particular location. So here I'm going to expand. So PG does depend on PE. Here it is over there. And so once we've set P and E, and here are two different examples. Here's an example where we have a groove, a V-notch, a teeth into the gripper teeth. And so typically if you have a V-notch and you're holding a circle, the pin is going to be centered along the axis of the V-notch. Most grippers that you will purchase will have interchangeable fingertips. So you can replace the fingertip with a fingertip of your choosing depending upon what you're picking up. And I think I've mentioned the previous day that you can experiment with where you want that V-notch to be and how deep the V-notch should be depending on what you're picking up. And you can first make them using 3D printing and try them out. That's a very quick and easy way to figure out what's a good shape of your notch in the gripper teeth. And once you're satisfied, you can then machine those teeth out of a much harder alloy, because typically you're not just picking up one part. You're going to be picking up hundreds of such pins or whatever have you. So if you were just using 3D polymer parts, they would die in no time. So here's an example where you, the robot designer, as the user in this particular case, I should say, you've picked the notch to be located here. You've also decided that you want to pick up the pin without the bottom of the fingers touching the table. Okay? It could be problematic that if you don't have everything accurately positioned and it touches the table, it might cause some impact, some jarring. It's always better not to make contact with the surface if there's no need to. So in this particular case, notice the fingertips are removed from the end of the table and they end up at some location, in this particular case, may be at the end of the fingertips, but notice the fingertip is not touching the table, while here this alternative, it is touching the table. Again, it depends on what you're doing. Now, here's the big issue. E is not simply pointing to a position XYZ, it also captures an orientation, a homogeneous transformation matrix. Remember, the upper right 3x1 represents the position of where it's pointing, but there's a 3x3 rotation matrix that tells you what the orientation is at that location. And in this particular case, we want Y to be in this direction, X in that direction, and Z in this direction. And therefore, PG also has to capture this same orientation. PG is not just a vector, it's a homogeneous transformation matrix. And so it captures both position and orientation. And in this particular case, I'm actually drawing the orientation that's captured in both E and PG. And by the way, I'm not drawing it twice, but I could draw it twice. There are two of them there, and they're both E and PG are pointing to the same blue orientation vector, the coordinate frame. And if I chose to point E and PG, if I chose to bring it, the end effector down to the original fingertips, then again, E and PG not only capture position, they capture the orientation matrix, the 3x3. And again, I'm just, there really are two of them, one captured in E and one captured in PG. But if I drew them both, it would just confuse things, too many lines crossing each other. So a lot of the diagrams I've drawn for you, don't show those orientations. They don't show all that information. If we go back here, where are they? Well, they're all as drawn, and this basically makes it clear, we're just drawing the vectors, but inherent in these homogeneous transformation matrices are the rotation matrices as well. So keep that in mind. In this case, we draw them just to explicitly make it clear that we're only drawing the vector portion, but they must also take care of the orientation changes. And that's what PG and the homogeneous transformation matrices allow you to do. Again, I want to point out E may be fairly trivial for a gripper end effector, but E may be rather complicated depending if it is a welding torch. The welding torch may not be pointing straight out of the flange. It may have all sorts of angles in it. Again, so keep that in mind for different applications. An applicator that puts down adhesives, who knows what the geometry of the end effector is for different applications. So again, assuming that PA is going to be a position above P, very simple definition. It's just an identity matrix because it's just offset from the original P by a distance Z, which you can see in this diagram. Here is P. Here is x, y, z associated with P from the base coordinate system. And just going straight up by whatever distance Z, we're going to define the approach position. Keep in mind it's a pose. It's the approach position and orientation of PA. Okay, so this PA is just offset by Z. So this is a very simple homogeneous transformation matrix. We're not asking for any change in orientation. We're simply applying an offset in the Z direction. If you want a departure point, which is often Never Never Land, if you don't want PA and PD to be the same, and you have some reason that PD should be something different, you can just set up your equation again. ZT6E, again, is the product of three homogeneous transformation matrices. It's going to be equal to P times the departure position, which is relative to P times PG. And all we have to then do is pre-multiply both sides by the inverse of P and post-multiply both sides by the inverse of PG. That's what you see over here. And that will get us calculate PD. So again, once you've moved it around to where you want it, you can capture what PD should be. And if we look at the diagram, here's the gripper, here's E, and some arbitrary place that you want that pin to go to after it's been on the table and was defined as PD is relative to P, but then notice here is E, which is attached to the gripper, and that points down to here. And so PG is going to take us, so here we have E, which is attached to the robot itself, and PG is basically, think of it as closing the loop. It points to the position and orientation of this point, but relative to P. So we're going from P to PD, and from PD down to where E is pointing to. So there's an orientation and a position at this particular location. It can get more complicated because as soon as we have a block B, where is B in this world? And then I'm just going through the steps so you get some sense of how this all plays together. If there was a block and there's a hole with respect to the block, so H is with respect to B, and then there's some insertion point inside the block, which is relative to the hole. And then we still have a PG to close the loop with that E over there so that PIN and E are essentially closed up. So B is, if we now, basically in order to calculate B, we're going to basically pre-multiply, we're going to basically post-multiply ZT6E by the inverse of H sub I multiplied by PAN, that's the insertion position relative to the hole, times PG. So in other words, we put a bracket in front of HI and a bracket of, after PG, take the inverse of that, and then essentially pre-multiply this side, post-multiply this side to get what B is. And then H sub I and pin are going to depend on your CAD model. It depends how deep do you want to insert that pin into the hole itself, and where is the hole on the block. Again, you can then, once you've got where the block is, you can define these terms in here and to calculate and position the block. So let's take a look. This is where the diagram gets a little bit messy. And again, I'm blowing things up dramatically so you can see the various elements. We've got the block coordinate system over here. And H is a homogeneous transformation matrix that defines the coordinate system of that particular hole. Okay, and that's this red. I'm just drawing the orientation, y in this direction, x in this direction, and z in this direction. as representing the hole's coordinate system relative to the block. Okay? So again, Z is going, and always right-hand rule, you can put your fingers along the X and Y, and Z goes into the hole itself. And then we have this pin, and initially, we're going to basically, if I have a block, and just imagine a block on this tabletop, and here's the pin, before I start, I am going to take that pin and manually put the pin into the hole to the right insertion point, and then I'm going to bring the pin down and grab it where I expect to be holding it. And so now I know where it's ultimately going to end up inside the block. So essentially what we're going to see, notice PIN with respect to the hole. That's essentially how deep I'm going to be inserting the pin with respect to the coordinate frame of the hole. Notice that the XY plane is on the surface of the block, and PIN is going to basically just be a certain depth into the hole with respect to the XY plane. So that's a certain depth, but keep in mind that the gripper E is holding the pin outside the hole. It's not, obviously, if the pin is inside the hole, there's got to be a part of the pin is still hanging out, and our gripper is holding the pin at that location. So essentially, PHA is the approach position of the pin location with respect to the hole, and in this particular case, we're saying that the distance is h from the surface of the hole to PHA, to this position PHA relative to the hole, and then we're going to be basically putting it in, and when it's in, this is the location when it's in the hole, and this is the location when it's away from the hole. So in effect, we can now move through the motions. Once we have this done and we have this set up, we can essentially work our way, given all the appropriate approach points of PA with respect to the pin, PD, PG, but we also have now the PHA and PIN that we add to the mix. And again, keep in mind that these different A's, B's, H sub i's are homogeneous transformation matrices. They are not just vectors, and so I'm not drawing all the coordinate frames you see here. So PHA is defined over here, and there's the minus H. That means it's offset from the hole. Remember, PHA is with respect to the hole by minus H. So we're going minus H because Z is going into the hole. Minus H is taking us away from the axis of that particular hole. So this is the task. And whoa, you're going to see all these matrices coming up. And we're going to group some of these matrices soon, and they play a very important part in your typical program for writing out a program internal to the robot controller. You as the user of the robot are never going to see this, okay? This is going to be captured in the syntax and on the tablet that controls the robot, or the code that you're writing. You won't see all this detail, but I'm writing it out so you see the steps that are going to have to be captured inside the robot controller. So remember, the first position, we're really moving to the approach point above the pin. Okay, so again, we can go all the way back to show all the closures going on. We're going back to all these steps, and we're capturing now all these parameters that you see here that we've introduced. But this time we're laying it out step by step. So now this is where we move to pin P1, which is at the approach position and orientation above the pin. Now we're going to essentially move down to the pin's coordinate frame, which is sitting on the table. We are going to close our fingers around the pin. We're then going to move away from the tabletop to a departure position, again, somewhere above the surface of the table. Then we're going to rotate around to a new position, and that's going to be the approach position and orientation above the hole, which is with respect to the block. And again, PG and E inverse travel along with it, because otherwise we don't have an equation. And then we are then going to insert the pin. We're going to move into the block to PIN, the homogeneous transformation matrix inside the block, which is defined with respect to H, which is defined with respect to the block. We're going to let go. We're going to let go of the pin, and then we're going to move away from the hole back to PHA, which is that approach position and orientation with respect to the hole, and then we can rotate back around to pick up the next pin, which may go into the second hole or the third hole. You know, you don't have to think of just blocks. They could be pallets. They could be pallets with slots in which you drop bottles, for example. Again, I'm just picked a pin and a block just to give you this image of what we're talking about. But now the question is, why did I set it up in this particular way? Notice that we have T6 on the left, T6 again, T6 again, T6, T6. Because at each one of these steps, I am going to solve for the inverse kinematics of T6. Remember, T6 is a 4x4 matrix. And when I solve for the inverse kinematics, what am I solving for? I'm solving, because I'm calling it T6, I'm solving for the 6 joint angles of that particular robot. I'm solving for the 6 joint angles. So each step here represents another solution. In order to move step 1 to step 2, I'm moving my manipulator above the pin, I'm moving it down, I'm closing on it, I'm moving away, I'm moving over to the block, I'm doing whatever I need to do to get it rotated above the hole and then inserting it. But each time I do it, I'm solving for the inverse kinematic equations given the 4x4 matrix represented by T6. So T6 is the glue that holds all this together, if you will, and it represents what I need to solve each step of the way. So notice, again, there is a common form here. Notice at the end there's always a PG E inverse, PG inverse, PG inverse. And on the other side, notice I have Z inverse P, Z inverse P, Z inverse P. We can essentially group these expressions, and essentially T6 is going to be equal to a local coordinate system. That's the coordinate system pointing to the block, the pin, the whatever it is that I'm working in, the relative coordinate system. Then there's going to be a set of positions relative to that local coordinate system. And then last but not least, every time I change the tool, I have to have a mechanism for capturing the tool information. So it could be I'm changing fingertips. It could be that I remove one tool, one end effector, and mount a second end effector for whatever reason. Okay? This is essentially going to group it all. So COORD is a homogeneous transformation that represents the local working coordinate frame. POS is the desired position of, call it the tool tip or the object that I'm trying to move around. And tool is the transform for describing that tool tip or the object. In other words, every time I change E, I'm going to have to change the tool. So essentially, notice the two forms. I can basically have T6 equal to this form, which matches what you see here, or I can rewrite it in this form, which basically shows you here's T6 multiplied by the tool coordinate frame. So this is going to represent the position and orientation of my final E, and this is the local coordinate frame, and POS is going to be representing whatever the position is and orientation. Remember, each of these is a 4x4 matrix, so this is going to represent the product of a 4x4 matrix, which is going to be equal to the product of this 4x4 matrix. So now I can change my program, and in a typical program, you're first going to attach a tool. You're going to decide what my tool is and where the notch in my tool is going to be. Or I'm going to attach an adhesive applicator, and so it's going to be a different E. Or I can attach whatever it is that I'm doing with the tool, I'm going to have a different value of E, but we're going to include the PG inverse, which is going to help us match up the coordinate frames. Then we're going to have to set up what is the local coordinate frame that I'm going to be working on. And again, you decide as the programmer where you're going to be working. Are you going to be working around where the pin was originally located? Or you're going to move over to the area around the block and the hole. So at that point, you're going to have a different coordinate frame. So we start off attaching a tool, which means I have to tell the controller what my tool characteristics are. What is E times PG inverse? I'm going to have to tell it what my original starting up coordinate frame is. In this case, the pin is the master of it all. I first move to P sub A. There is P sub A. Then I move. Notice I am moving to a location which you might call the identity matrix. In other words, we are moving back, in this case, down to the pin. So when I'm up here, remember PA is with respect to where the pin was originally on the table. That location was P. PHA is relative to pin, so essentially when I'm moving down, because P sub A is relative to the pin, this is just an identity matrix over here. Okay, because we've redefined the coordinate frames in terms of that pin, which means this is essentially what you see here. You don't see anything here because it's an identity matrix. We're simply moving down where we define that frame to be starting from. Now we close our gripper, we move away. Again, notice PD, there's no P in here. PD is respect to P, but that's captured in CORD. Notice CORD, it's Z inverse times P. We've shifted the coordinate frame. We've shifted the coordinate frame from where the robot is defined in the world coordinate system. We've shifted the coordinate frame to where the pin is on the table. So everything is now done in terms of that local coordinate frame, which is Z inverse P. And if we're going to move over to the block and the hole, we redefine the coordinate system. This time, the hole is the center of the world for everything that's relative to the hole. And so in this case, we change the coordinate system to Z inverse BH. We move to PHA. Notice that's the approach point above a particular hole H sub I. Tool hasn't changed. We're still using the same tool in this particular case, which we've defined up here. So the tool hasn't changed. And then we push the pin into the hole to a depth. And that depth is defined in the homogeneous transformation PIN, which again is relative to the hole. We let go of the pin, and then we move our robot away back to the approach position above the pin. That's over here. And again, at this time, at this location, this is what T6 is equal to. I'm just pointing out the steps. We're just going back to this. and then we can just circle our way back around to the very beginning in order to pick a robot again. And here I'm just pointing out this origin is essentially at this location because we've redefined the local coordinate system with respect to where the first object was located. Okay? It's important to recognize, if you remember the Puma robot, we had a coordinate system originally, and go back and look at that. The coordinate system is, the E is defined, we essentially have a wrist rotate, we have a tool rotate, so we have 3 coordinate systems, and depending on where we attach the end effector, we're going to shift E further out and shift it to where we need to be in order to pick up an object. And if the gripper has some V notches in, it's usually a good place for gripper teeth to close around a circular object. If the object is not a circular cylinder, it could be anything. It might have some notches in it. It might have some steps in it. Wherever it is, I'm just looking around, different objects have different shapes. And so you're going to have to, if this is the object you're going to pick up, again, how are you going to pick it up in order not to mangle the wires? So you as the user must have some sense of how you want to pick that object up and decide where on the object you're going to pick it up. And so you're going to find a local coordinate system associated with that object. So for every object you're going to be moving around, you want to define some local coordinate system with respect to it. And I might back to the welding task, the adhesive task. The orientation of that task becomes very important because you're going to be traveling, along one of the axes while you're welding. So if I'm welding this shape over here, I'm going to have to make sure that that axis is defined properly so that I can create a path, all with respect to the first position, and work along and make sure the orientation of my welding torch is aligned based on how I want it to be aligned. So again, E is not just a position, it must also include the orientation of that applicator or the orientation of the torch so that it is doing the job that you want to do. And again, you've got to be an expert on the application, otherwise, why are you programming the robot? Anyway, I'm pointing that out to you all. So that's what we're talking about when we're talking about programming languages, okay? There are pretty sophisticated languages out there, and then today we live in a world where everything seems to be done on your phone, or we use tablets. But way back when, amongst the very first languages for the Puma robot, there was something called VAL, which stood for Variable Assembly Language. It had a certain number of commands, and you can read more about it by just going to a Wikipedia listing for it, where it goes through. There's a monitor, an editor, positions, and program. I'm not going to go into all of this. There's no point. There's no need to. But the message is as follows. How do you define these positions and orientations in space? How do you edit your program? If you're developing a robot control language, a syntax, you need to not just think about the program that does motion, position and orientation here, position and orientation. You must also be able to edit your program. So how are you going to edit the program? How do you list programs? How do you print them out? Where do you store them? How do you store them? How about controlling your program? Slow it down, speed it up. Again, that has to be part of the commands that are built into the robot controller. You want to check on the status of various things. System switches Maybe you want to be able to turn certain things on and off while you're doing stuff. For example, in the assembly of that flashlight, you really want to make sure that you don't clamp on the flashlight head unless there is something inside there, because I can't tell you how many clamps we destroyed, because if it doesn't have something to clamp on, it deforms the whole clamp. And so I think I had a previous teaching assistant going back 3 years ago who basically bought a LED photosensor that we drilled a hole on the side of the clamp, inserted this LED photodetector, and simply designed a program so if there's nothing in it, that LED will prevent the clamp from turning on. In other words, there are solenoid valves, and the solenoid valves have to turn on in a certain sequence. And if that LED doesn't detect presence of something which blocks the light, it won't allow the clamp to close. So the appropriate solenoid valves are triggered. So that might be something called system status and control, system switches to turn things on and off. And there needs to be a way of diagnostics to know, hey, what was going on here? Can I actually see what each motor was doing or what each joint is doing? What was the joint velocity here or there? Again, today we have a wealth of opportunities to evaluate and test because you are writing the Python program that's doing a lot of this thing. You are not using the raw commands on the teach pendant of the UR5, which I find, I don't know, don't quote me, but I don't find that as a really good human interface for programming robots, to be honest with you. But the bottom line is it represents one mechanism, one approach to how users of the UR5 use the teach pendant to set up a series of targets, and they basically go from target to target. Robot configuration control may simply be, do I want my elbow up or elbow down? Do I want my wrist up and down? So there's configurations that need to be set up depending on the robot itself. Motion may involve, am I going to do joint interpolation, world coordinate interpolation? How do I move around in space? And I have to define it. Hand control has to do with the gripper and how we control the gripper. And then the mathematics of moving everything through and assigning things. Again, I don't want to go through all these different steps. You're not going to use this robot ever, so there's no point. But in this world today, probably, should I say it's the state of the art? It represents what is used today. The robot operating system is a generic system for programming robots. Because it is so broad and so wide, it is just has so many things in it. It takes forever to really get a good handle on it. It's been around for a while. You can see originally developed by Willow Garage, which is a company that doesn't exist anymore. I don't want to go into all the details, but it's stored in GitHub. GitHub, how many people, all of you should have heard of GitHub by now, essentially a classic place to put stuff which can stay theoretically forever, who knows. But the point is, ROS is one environment, but it is so big and so monstrous, it takes forever to really figure it out. So you need to be very careful about using ROS, and you really need to understand it to take advantage of it, because the neat thing about ROS is there's code that you can reuse. If you find code in ROS, it's open source, you can take advantage of it and use that piece of code for your particular application or for your particular development. So you have to understand its purpose is really so you don't have to reinvent the wheel all the time. I notice it's 9:10. Why don't we take a break? I know I need a drink of water. Why don't we take a break for 10 minutes, and then we'll pick up and do a little bit more before we're done for the day. Okay, so let's take a break. It's 9:11 now, so we'll meet at 9:20, 9 minutes from now. Thank you. Okay, I was just checking my email, and I had several more students ask for printed copies this coming Thursday of the exam. How many people in this room are going to want printed copies? Oh, a lot of you. Send me an email. I'm not counting how many heads are here. Send me an email, and just based on your emails, I will make sure to have sufficient number of printed copies for you here. So again, if you don't send me an email, there's not going to be a copy available. Okay? All right. Let's continue with our discussion about programming robots. It is not as I hope you've begun to learn in the labs that you're doing, that predicting what exactly is going to happen with your robot when you program it, it is not so straightforward, number one. The positions and orientations that you are going to set up in your offline programming don't seem to match the real robot's position and orientation. And so there is a problem that you're going to have to face no matter what robot you're using. There's just inconsistencies, inaccuracies. You don't know how old that robot is. And when I say old, I don't mean in terms of age. I'm talking in terms of how many uses has it gone through, how many cycles, how many times has that robot collided with something that you didn't know about. Every time that robot or that gripper or that elbow or something hits a surface, we're going to have a problem. Something may have been screwed up internally, a tooth somewhere may have been damaged. You just don't know. And so it's really, as soon as you deal with a real machine, you're dealing with unpredictable kinds of things. It's not like you're writing, everything is in simulation, and you're writing a program and you're controlling a simulated robot. The simulated robot is always going to do what you tell it to do. The real robot is not necessarily going to do what you tell it to do. And so there are going to be unpredictable things happening. And if you make a mistake, and everyone is human, people make mistakes, you may collide with something. And so you have to build in safeguards to protect the robot and protect the world that you are dealing with. And once it hits something, you can't just reverse it. It's been damaged. You need to fix whatever was damaged. And so this notion of being irreversible is there's not much you can do about it. Once you've collided, it's collided, and you have to sort of figure out what was the effect of that collision and how can that be corrected so the next user, i.e. another student using that robot, doesn't have to deal with your problem that you created when using it. Okay? So I think that's in this environment where you guys are all using robots in a lab, you know there are other students that are going to use your robot afterwards, and just your own experience programming that robot. I am sure some of you hit those probes against that granite block along the way. I'm sure some of you damaged those probes in some sense. I don't know, but I can guess it happens. And in our world, we've designed it so we can replace the probes. But there may be parts of the robot that are not replaceable or can't go back to where the condition, the pristine shape it was before. So these are all issues when you're dealing with the real world that don't exist with a simulation. In a simulation, you can reset all your initial conditions to 0, and boom, you can start it again. In the real world, that doesn't happen. And we need to take into account, the speed, how fast things are moving, their acceleration. We're going to have to create via points. I am sure that when you start working with the UR5 for assembling that flashlight, depending upon where the robot is, where the robot end effector is, you're going to find you might have to add some via points because the singularities of the UR5. The UR5, as you saw, a few lectures back has some really unusual singularities. Unusual in the intuitive sense. You really have to look at that robot carefully to figure out where those singularities are. But intuitively, you wouldn't guess that you were running into a singularity until you try it. And then you're going to have to go back and say, why did it get stuck there? I didn't expect it to get stuck there. And so you're going to have to think, maybe go back and look at those singularities in the lecture from a few lectures back and say, I better move it here so that I can still get the robot to do what I want it to do while it's assembling. And then types of motion, straight line motion, curved motion. Are we dealing with joint interpolation? Are we dealing with Cartesian coordinate motion? Those are all issues. And we have not even begun to talk about controlling forces. Because at some point, and we are going to do this, we are going to intentionally want to collide with the surface. There are sometimes you want to mate one object with another, which you are doing when you're threading parts together. But when you thread them slowly, and I do suggest, I don't have anything that I can thread together, but look at two objects that you have at home and just try threading them together. How do you start the thread when you're coming at it at an angle? What kind of angular offset can you have and still start the thread? And how much inaccuracy can you have when you have the two parts to come together? You don't want to damage the thread. You don't want to force your way into the thread, because I can tell you that's going to damage the thread. And I can't tell you how many old flashlight parts we've thrown out over the years. Boxes of them. And so we have enough for you guys, I hope. But the bottom line is you have to think through, because you are going to hit. There's going to be a collision. And what you want to do is guide the collision and think what you're doing as they collide. And the robots has a force torque sensor, and the joints can tell you something about what those torques are and how much forces you're applying while you're doing the task, and then you need to control them. And a lot of it has to do with what sensors you're using. How many sensors are available to you? How many have you incorporated either in the robot or externally through other means? Each sensor provides you with a different piece of information, and that sensor could be inertial, it could be off to one side, or it can be built into the robot itself. And in fact, the latest versions of the UR5 are called the UR5E, because they integrate a force torque sensor into the last joint. So you don't have to buy that as a separate widget, which is on all our robots. All three of our robots have the force torque sensor from robotics separately. And my understanding is that UR basically uses the robotic sensor in the UR5E. They don't advertise that, but I happen to know that that's the case. So here I would like you to see this particular video, because it illustrates a very complicated task that I would imagine anybody, and it doesn't have to be a mechanical engineer sitting in their senior or graduate class on robotics, will understand. I'm assuming you guys do this somewhere along the way, and here we have a robot trying to mimic what you as a human can do easily. But I want you to think, as you watch this robot do this, I want you to think, how would you write the program to control the robot doing what you're going to see over here? Okay? So let's start with the video. Is there an, I don't, that's good, there's no ad. Okay, this is slow going, because this is operating at 50 times the speed. You are seeing something that is happening much faster than it really is occurring. What's it doing here? figure out where to grab the towel. Think about the program that goes along with this task of folding laundry. Again, this is accelerated 50 times as fast as it really is occurring. Look at the gripper orientations. And how hard do you tug so you don't tear the towel or the face cloth? I never saw these towels before. Okay, you get it. So let's go back. This particular robot doesn't exist anymore. I do suggest you go look at this website. This is robots.ieee.org. And you can actually see different robots. I'm now, with my cursor, moving this robot around so you can see some of the capabilities. There are different views. It does have a vision sensing built into it. But it was designed in 2010. Okay, this shows you some of its inner workings. This is not a new robot. It's been around a while. And so if we go to the main website, you can find a lot of old robots by name. I still remember the Exo is an exoskeletal robot. Companies out in Berkeley, California. Robonaut is a NASA robot. I've used several of these for exams over the years. I'm just looking through. I haven't seen some of these in so many years. This was the original Google self-driving car. AlphaDog was on an exam years ago. So was Animal. That was on an exam years ago. There's the Atlas robot, the old version of Atlas, the newer version of Atlas. So this is a good repository of lots and lots of different robots from around the world. We're just at the C's, just to give you an idea. We can just go on. And just looking if I see any other robots. So there's the LBR IIWA robot that we've talked about in class. I'm curious, soon we should see the Puma robot. R's, Q. Not sure why the Puma's not here. Could be here under a different name. Anyway, you get the sense. There's the UR robots over here. Oh, Unimate made the Puma robot. But this was an electrohydraulic robot. The Yumi robot's been on an exam. Okay, you get it. Let's close this. Let's close that. Let's go back to here. So the bottom line is we have a complicated world. And online programming usually talks about interacting with the actual robot while you're programming it. The problem with this is you have to have the robot that's accessible to you. You must have the robot there so that you can program the gripper, program the joints, do everything. And what's bad about that is you're tying up the robot when it could be used for production. So think for a moment if I had, 52 students in this class all trying to program, instead of having a pre-lab and using RoboDK, just imagine you each had to have access to the robot to doing your thing. There just aren't enough hours in the day. We wouldn't have enough robots for you to be playing with in order to do programming. So the bottom line, online programming is not the future, and that's why RoboDK is an incredibly useful offline simulation tool. A very important tool. It doesn't require the robot. But, you know, the big problem with offline simulation is it doesn't handle sensors very well. How do you simulate a vision sensor? How do you simulate a force sensor? That creates all sorts of other issues. People have worked on this issue, but I can tell you right now, very limited capability to actually simulate a real sensor, because sensors have also inaccuracies, repeatability problems, you name it. The sensor itself has issues. How do you build that into the offline programming world, that it represents the problems of that particular sensor? And just like robot manufacturers don't want to tell you everything there is to know about the robot, the sensor vendor doesn't want you to know everything there is about the sensor. They want you to know how ideal it is, but they don't want you to know that, you know what, it has limitations and it's not going to tell you everything you expect. So we're getting into, clearly offline programming requires very sophisticated software in order to do that. This is a really good website on lists of robot simulators. And if we go down and look, you'll see, let me see if I can increase the size of that so you can see it a little bit better. Notice there's RoboDK, your favorite software. Now it's proprietary. That means you can't get to use it unless you have a license to use it. We are very fortunate. I was able to negotiate with RoboDK. They're located, by the way, in Ottawa, Canada. And for quite a number of years, they've given me free licenses for this class, because they want you guys to use it, love it, and then one day when you work for someone else, going to tell your boss, we need to buy RoboDK. A few years ago, I asked them who in Minnesota is using it. They not allowed to tell me, but they said there is a manufacturer in the state who's using RoboDK, and I'm not allowed. I think I know who it is, but I'm sworn to secrecy. The bottom line is it's proprietary. It's not open source at all. You must have a license for it. And again, RoboDK uses OpenGL, so graphics is pretty straightforward. You see the whole image on here? Yeah. And it works really well. If we look at technical information about it, notice its main programming is Python. Most other languages, simulation worlds, are C++ and or Python. Some of them are even more complicated. They support a variety of different worlds. Again, I'm not going to get into all these, but it does. RoboDK has tie-ins to API, so you can plug other things into it like we do. And so you can plug Python. You can attach C# or MATLAB to it as well. And it has its own GUI, its own graphical user interface. If you take a look at its support, I'd say it's pretty good support. It works so well for us that we haven't bothered them in years. And initially, we had to sort of tie into them, but not since. We haven't had a question about it in all these years. It's just worked pretty well. Point out a couple of things. There is a dynamic collision avoidance application in it. You should have played with it somewhere along the way. I won't go deep into it. Certainly offline programming. Notice, though, if we look at RoboDK, it's not meant for mobile robots. It's not meant for drones. It's not meant for underwater. It's strictly designed for robotic arms. Or, yeah, I would say just robotic arms. That's manipulators, or its bread and butter, and that's it can pretty much talk to most any robot manipulator that's out there. And anyway, you get some pretty good idea. Notice sensors that are supported. RoboDK does support stereo sensing, depth cameras, omnidirectional cameras, etc. 2D laser scanners. It gives you some idea. This other group, odometry, IMUs, GPS, they're really for vehicles. And again, RoboDK is not a vehicle-oriented simulation package. So, with that, let me go back to the, that's about all I want to talk about offline programming. We still have some time, so I'm going to start the next topic that we're going to be talking about. And the next topic, we're going to go back to Jacobians. If you remember, we talked about Jacobians before, but now we're going to get into how do we compute the Jacobian. And we're going to go through some tedious steps to see how we come to the point where we can make an approximation. And based on that approximation, we're going to be able to compute a Jacobian quite quickly. And in fact, if you go take a look at exam 2s over the years, I would say most exam 2s have a Jacobian problem in there. And again, the point is, based on what we're going to cover in computation of Jacobians, we're going to learn about all sorts of assumptions. And because of those assumptions, you can pretty much simplify the calculation of the Jacobian and come up with that 3 by 6, 4 by 6, 8 by 6, whatever it is, for the Jacobian that will let you do what? Remember what the Jacobian is doing? It's relating the velocity and orientation of the end effector in space with each of the joint angle velocities. So in other words, we're very much interested in the Jacobian because the Jacobian helps us relate the velocity of our hand in space, how fast it's moving, the direction it's moving, with what each of the individual joint velocities are saying. So it's a very important part of programming robots because there are many applications where the velocity of the end effector is critical. And we're also going to see, and again, I'm nowhere, we only got about 10 minutes, 12 minutes left in this lecture. It also is very important when we're talking about forces, and we'll see that the Jacobian plays a role in calculating some of the relationships between the forces at the end effector and the resistance inside the joints itself. So the Jacobian is a very important piece of the world of robotics. So we're going to get into that. And the next few lectures are going to be talking, obviously this Thursday's an exam. And by the way, in case I forgot to mention, there were several more people who asked for printed copies on Thursday. Don't forget to send an email. If you didn't send an email, you're not going to get a printed copy. So essentially, the next few lectures we're going to be talking about computing the Jacobian. The textbook itself has some material on it. I prefer the coverage that's covered in a textbook written in '86 by Asada and Slotine. And so I've used that as a basis for developing this methodology. It is just a different description of what you can also find in the textbook, whichever version of the book that you're using. So we're going to start off just by first breaking up the issue into two parts. Remember that when we're talking about the endpoint is a position in world space, xe, and I put little zeros, and you need to be careful when I have a zero and where I have a dot, but a zero is telling us it's in the world coordinate frame. Okay, we need to always keep track of what coordinate frame are we dealing with. So I've used 0 up at the top. again, because there's so many symbols down below and down on top, I just want to repeat that when we're talking about the end effector, the position of the end effector in world coordinates is going to be a function of end joints. And the joints, again, we could have prismatic joints, we can have revolute joints. I'm just going to generically calling them Qs. So there's Q1 through Qn, depending on how many joints there are. And the position of that end effector is with respect to the coordinate system, which is x, y, z, you see here. And this is the base of the coordinate system. I've used this little X, if you want to call it. It looks like an hourglass, whatever you want to call it. In my mind, that represents a pseudo-revolute joint. Imagine there's a revolute joint over here. Again, it could be something different, but it's going to allow a rotation about the Z naught. Again, it's just a schematic. So we might have another joint, a revolute joint at this point. There could be another joint. And I arbitrarily have written a whole bunch of joints, and each joint has a subscript I. And we need to remember, and this is again important even for your exam this week, that if we're talking about, this is theta dot I, that's the angular velocity of theta I. Remember, it's rotating about the coordinate system, which is I minus 1. So essentially, if I have a revolute joint for joint I, and that revolute joint is going to have a z sub I minus 1, the theta is going to rotate, theta sub I is rotating about z sub I minus 1, and the unit vector at that location, b sub I minus 1, is going to be pointing in the direction of z sub I minus 1. So remember, joint 3, for example, is rotating about z sub 2. Joint 1 is rotating about theta sub about z sub 0, if they're revolute joints. And if they're displacement prismatic joints, they're moving along z sub I minus 1. So this is joint I. And b sub I minus 1 is the unit vector in the direction of the joint axis. Notice I'm not saying it's a revolute joint, a prismatic joint. It could be either. But for a prismatic joint, it's going to move along b sub I minus 1. And if it's a revolute joint, it's going to rotate about b sub I minus 1. So here's joint 1. And then there could be a joint 2 and a joint 3, 4, 5, 6, 7, and so on, until we get to the end effector and the end point, which we're simply going to call E. And in this case, maybe we call it x sub E. And the reason we're writing x sub E, so we can break it up. X sub E is going to have 3 components. It's going to have an x, y, and z associated with it. So we're going to deal with x sub E, the endpoint in world space. And then after we've dealt with the endpoint in world space, we're going to talk about the orientations about the endpoint. And notice we're going to call this d phi sub E. This is going to be a set of orientation angles about the endpoint. So the ultimate, we're going to have 2 sets. We're going to have a 3x1 of where x sub E is in space. And then we're going to also have an orientation vector, which notice it's a different deal than we've talked before. We're going to call it d phi E, because we are going to assume that we're dealing with very small differential angles. And why can we do that? But when we're talking about controlling velocity, we're talking about very small increments in time. And if we're dealing with very small increments in time, we are going to basically say we're going to have very small displacements and very small changes in angle. And that property is hugely important, because we're going to see, as soon as you start taking trigonometric functions, sine of a small angle and cosines of a small angle, we're going to see a lot of terms begin to disappear. So that's a piece of what we're talking about. R sub I minus 1 is essentially going to be a vector, and it's going to be every joint on my particular robot is going to have an R vector, which is going to take us from the I minus 1 coordinate system and point to where that E is, where that X sub E is going to be in space. This is a 3x1 vector, and we'll see later that this is an important parameter in order to calculate joint velocities. Okay, so I specifically identify R sub I minus 1. So let's start by talking about, remember that Jacobian, I did it on the whiteboard behind me, step by step. This is the first 3 rows, okay? This is the first 3 rows of the Jacobian equation. And it's going to have, notice, it's the derivative of x sub e with respect to time. Remember what x sub e is? It has 3 components, x, y, and z. And so it's going to be the partial derivative of x sub e with respect to q1 multiplied by dq1 with respect to dt. And then we're going to have a component here that we're going to add all these components, and they're going to be n components depending how many joints we have. So when we add all these up, they're going to tell us what dxe by dt is. But remember what the Jacobian represents. It represents components, because we're going to split out all the dq1s by dt and create a vector, and we're going to have a matrix which has the terms of dxe partial by q1, then partial dxe by q2, and so on and so forth. For prismatic joints, we're going to see that this partial derivative of xe with respect to q1, if it's a prismatic joint, is going to be a very simple relationship. Remember, for a prismatic joint, what is qi for a prismatic joint? It's just the displacement, okay? It's just the displacement. So if I know my unit vector along the z-axis, we just multiply by the d sub I dot. What is d sub I dot? It's the velocity along d, okay? It's the velocity along d. That's a scalar. This is not a vector, but it's multiplied by a unit vector. So if I take a look over here, back to my little example, here's d sub I dot. That's the velocity in this direction. And if I multiply d sub I dot times the unit vector b sub I minus 1, what is that going to give me? It's going to give me 3 terms, right? It's going to give me the term along the z-axis, along b sub I, and also the 2 other orthogonal axes. But remember, b sub I minus 1 is a unit vector, so it's only going to have a velocity in one direction. So essentially, this is telling us the direction of the velocity of that particular joint multiplied by a scalar. So this is for all prismatic joints. If I have 6 prismatic joints, there will be 6 of these. 2 prismatic joints, there will be 2 of these. So prismatic joints have this form, but if it's a revolute joint, it has a different form. The angular velocity, remember we said over here, the angular velocity, the scalar value of that joint velocity is theta sub I dot. And if we multiply that by the unit vector, that's going to give us a vector which is angular velocity vector, which is simply equal to the scalar theta sub I dot multiplied by the unit vector b sub I minus 1. Okay, that tells us what the angular velocity is, but remember, we want to find out what is the effect of the angular velocity on the displacement of the end effector. The displacement of the end effector is basically, we're looking at the partial derivative of x sub e with respect to each of the joints multiplied by the joint velocity, And that is going to basically be equal to, notice what we're going to do. We're taking the cross product of r sub I minus 1, that's what this is, with the angular velocity. So in order to find out what the change in the endpoint is, the change in x, y, z, we have to take the cross product of the angular velocity, omega sub I, times, so this is the angular velocity. It's going to cause this vector to rotate. And when we take the cross product, we are going to get the result that tells us what the three components of x sub e, what this is. And it's going to be, we can replace omega sub I with this term, so we get that. Cross product with this term. So this is the result. It's a unit vector cross product with r sub I times the scalar theta dot I. I know we're over by a minute. I was going rather quickly this last few minutes. I will go over it again. A week from today, okay? A week from today, this coming Thursday, I think I've belabored the point, you have an exam. And so we'll see you. I will be here during the exam, and so will Robert. And so we'll be able to answer questions if you're in the room. And if you're not here, there'll be a phone number on the live streaming on below it, and you can call that phone number, and that's going to be directed to the phone of the operator back there. So we'll get those questions too. If the questions are private, I may basically we'll have a private conversation back in the operator room. Or if you're here in the room, I may walk you outside the room and you might ask me a question to me outside the room, and I don't want the world to hear what you have to say that might affect everybody else's exam. We'll see you on Thursday. Yes?
Are there any computer
Huh?
My laptop broke, so I can't use
Oh.
on there right now.
You know, we used to. I don't know what happened. First of all, you can come in, when there's nobody in the lab, you can use any of the computers in there. Number one. Number two, there are 3 robots.
Yes.
I think I'm messing
Look at the schedule.
Okay, I know how to do it.
Nick, I'm trying to remember if we still have.
Bunch of matrices.
We did ask for it at one point, but it just got with COVID and what's going on in this building, the labs upstairs. I don't know.
Okay.